Today's seminar is going to focus on solving systems of linear equations. Our goal and I can statements for this lesson are: I can solve a system of linear equations by graphing, I can solve a system of linear equations by substitution, and I can solve a system of linear equations by using multiple versions of elimination. Now, we have a few more than 3 I can statements, like specifically when you refer to your data tracking sheet. We have multiple versions of elimination that are listed, and we'll go through most of those today here in this lesson. So if you could at this time, pause the video and copy the title and the I can statements into your notebook so that they are there for your reference. And the foldable that you will need today will look like this. It is yellow, and it is about solving systems of equations. So we'll look at graphing systems of equations, look at using substitution with systems of equations, and using the elimination method when working with systems of linear equations. Now, really the whole understanding behind systems of equations is that you're finding the intersection point of two lines and finding the point at which the solution will satisfy both equations. So let's go ahead and get started with graphing. So we're going to have a couple examples here. So specifically, we have example 1 here, and the two lines that we'll be graphing, and as you can see they're in standard form right now, are negative x plus 2y equals 3 and 2x plus y equals 4. Now typically when you're asked to graph a system of linear equations, they're more than likely will already have the equations in slope-intercept form. So in this case, we're going to have to change these from standard form into slope-intercept form. So we're going to have an extra step here. Doesn't hurt to learn that. So let's go ahead and change this first equation then to slope-intercept form. So negative x plus 2y equals 3. Now remember, slope-intercept form is y equals mx plus b. So I'll just write that here. So that means we need to get y by itself. So the first thing that I'm going to do here is going to be to add x to both sides. That means these will cancel, and we'll be left with 2y equals x, since it's positive. This is a positive 3, so it says plus 3. And now what we'll have to do is divide everything by 2 in order to get y by itself. Divide by 2, divide by 2, divide by 2. So what we'll end up having here then is y equals 1/2 x plus 3/2, or that's 1.5. So this one's going to be a bit goofy, but we'll make it work. So that's our first line, switched over from standard form to slope-intercept form. And let's do the second one then. So 2x plus y equals 4. And I can already tell that this one's going to work out a little bit nicer. So first thing, let's move the 2x over to the other side. These will cancel. We'll be left with y, and it's positive, equals negative 2x. Since this 4 is positive, we're just going to say plus 4. So that one actually works out a lot quicker because we didn't have to divide anything since the coefficient on y was already 1. So now we are going to graph both these lines and find their intersection point. And hopefully it won't be too difficult given that we have kind of a goofy fraction here. We'll do our best. So this line I'm going to graph in red, and this line I'm going to graph in blue. That way we'll be able to see the differences. Now, one important thing to note here is that when you're graphing these, when you have two lines, you have to be precise, because if you're not precise, you're not going to find the exact location that they intersect at. You might be off a little bit. So let's hope for some precision here and hope this works out for us. So plotting this first line is going to be a little bit goofy because our y-intercept is 3/2, which is also 1.5. So I'm going to do my best here to plot 1.5. So right in between here. And sometimes this happens where you have to plot like this. It's not always a nice whole number. Then we have to plot 2 other points. So if I go down 1, I'd be at 1/2. And then over 2 would put me here. So hopefully I'm a tad bit accurate. And now if I go down 1, I'd be at -1/2, and over 2 would be here. Then we'll need to use our straight edge and draw a line through that and be as precise as possible so that we can get the location at which they intersect. Okay, so first line is drawn. Now let's do our second line. So it looks like we're plotted up at +4, so 1, 2, 3, 4 is our y-intercept. And hopefully you can see that. You can zoom in here a little bit more. Yeah, that's better. And then let's go down 2 and over 1. Down 2 over 1. And we will put a line through that. And this is going to, of course, not be very nice. So the point of intersection that we have is right here. And I need to look real quick to see exactly where that is because it didn't come out to a nice whole number, or 2 whole numbers, I should say, for an x and a y point. So I'm going to go ahead and check this real quick and see exactly what they came up with. So bear with me real quick. Okay, so I see the problem the mistake that I made, which is that I went down 1 and over 2 instead of up 1 and over 2. So that red line we need to replot, and I do apologize. So still at 3/2, which is 1.5, and we need to go up 1 and over 2. So we'd be at 2.5, then we go up 1 to 3.5 and over 2. So I made a mistake as well. I do apologize. So our actual red line is going to go this way. And this gives us a nicer point of intersection. So this other line, this is not correct. See, even I make mistakes, and that is okay. So now this actually gives us a much better point of intersection. We are at the point, which is going to be right here. And that's the point 1, 2. So their point of intersection, I'll put over here, is 1, 2. That's the solution. So if I were to substitute 1 and 2 in for x and y into each of these equations, the first one would equal 3, the second one would equal 4. So that solution satisfies both equations. So again, I'm sorry for the mix-up there, and hopefully in the second example here, I can redeem myself. So sorry for the confusion, like I said. Alright, so first and foremost, these aren't in slope-intercept form, which kind of irritates me because usually they already are when you're asked to graph a system of linear equations, but it's okay, we can just change it, not a big deal. X minus y equals 5. So remember slope-intercept form, y equals mx plus b. We're trying to get y alone, so I need to subtract x from both sides. That x's cancel on the left-hand side. Negative y equals negative x plus 5, since that's a positive 5. Now we're not done here yet because this y is negative, so we have to get a positive 1y. So in order to do that, we need to divide everything by negative 1. And this would give me a positive y, and that will equal a positive x because it's negative 1 divided by negative 1. So I'm just going to say x, and then it's going to be minus 5. And hopefully I did my work correctly there so we don't have another graphing problem. Alright, second one then, let's do the same thing. 3x plus y equals 3. Going to subtract 3x, subtract 3x. That cancels. We're left with y equals negative 3x plus 3. So we have both of our lines, both of our equations converted from standard form to slope-intercept form. Now we can go ahead and graph them since we know the quick way to graph using slope-intercept form. So again, this first one I'll make red, the second one I'll make blue. So this says y equals x minus 5. So that means I need to plot my y-intercept at negative 5. 1, 2, 3, 4, 5. And it's going to be in a goofy spot on your graph. It's going to be kind of tough to see. So way down at negative 5. And your slope is 1 over 1. Remember, there's a 1 over 1 there. So up 1, right 1, up 1, right 1. And that'll be sufficient. Use my straight edge in order to be accurate. And then graphing my second line, it looks like we're up at positive 3 for our y-intercept. So 1, 2, 3. And then you're going to go, your slope is down 3, right 1, down 3, right 1. And as we can see, that ends up at an exact point on your first line that you graphed. So this one works out nice because I did it correctly this time. Alright, now the only other thing we need to do is write the solution. So the solution to this one is a coordinate, and that coordinate is 2, because that's my x value, negative 3. So again, if I were to put these into this equation, if I substitute those back in, they should satisfy those equations and make them true. For instance, if I take this 2 and this negative 3 and I put it in this first one, I have 2 minus negative 3 equals 5. Well, that really says 2 plus 3 equals 5. So that worked out. And if I were to do the same here, and I put 2 and negative 3 in for x and y, 3 times 2 is 6, plus negative 3 is 3, so 3 equals 3. It works out. We know that this is the correct solution. So you can always go back and check that solution in your original equations in order to make sure that it works out. So that's systems of equations by graphing. Let's move into the more algebraic side of this then, because sometimes we're not always given a graph. And our next thing is called substitution. And I shouldn't say thing. Our next method is substitution. And the best time to use substitution, in my mind, is when you have something already solved for x or y. We can take what's solved for it and we can substitute it into the second equation in order to have an equation in one variable. Then we're able to solve for that variable and ultimately use that value to put back into one of our equations in order to solve for the other one, hence getting the solution to the system of equations. Now that was a mouthful, but I'll show you what I mean. So in this first case, we have something that's solved for y already. So I'm immediately thinking I'm going to use substitution because it's going to be a efficient method for solving this system of equations. So I know that y is the same as or equal to 2x plus 5. And I have a y in the second equation. So instead of using y, I can use this 2x plus 5 in place of this y because they're equivalent. That's what the equal sign means. Y is the same as. So this 2x plus 5, I can take and replace this y with it, and then have an equation in just x. So let's go ahead and substitute that in then. So my new equation would look like 3x, because that's going to stay, and then I'm substituting 2x plus 5 in for y. So I'm going to say plus 2x plus 5, and that's equal to 10. Now it's just going to be a matter of combining like terms. Oh, here comes that topic again. Remember, that's still here. And then we're ultimately going to have an equation that we need to solve. Oh, there's that topic again as well. Those things don't go away. They stay. So the first thing I'm going to do here is I'm going to combine like terms. I see a 3x and a 2x. So that's going to give me 5x. And then I'm just going to rewrite everything I still have. I still have a plus 5, and I still have an equals 10. Now it's just a matter of solving for x, so you have a two-step equation. So I'm going to subtract 5 from both sides. These will cancel. I'll end up with 5x equals 5. Then we're going to need to divide by 5, divide by 5. And x will equal 1. I have half of my solution figured out already. So if I go up here for I'll put it over here, my solution, I know that x is 1. I solved for that. So now I need to find y. So I can use substitution again and put this value of 1 in for x in either one of these equations. Typically I look for the easier one to work with, and I think I'd rather work with this one that's in slope-intercept form. So if we say over here y equals 2x plus 5. I'm going to substitute, so I'm going to use this little arrow thing again that we did. I'm going to substitute this 1 in for x, because it's the same thing. We know that x is the same thing as 1. So let's rewrite this then in order to solve. Y equals 2 times 1. Remember, a number next to a variable is multiplication. And then plus 5. So let's go ahead and simplify this then. Y equals 2 plus 5, y equals 7. So I know my y value here now as well. 7. So this is my solution to this system of equations. Now if I were to plug this 1 and 7 back into both of these, they should both work out. So if I put 1 in for x, that's 3 times 1 is 3. If I put 7 in for y, that's 7. So 3 plus 7 is 10. That works out. If I put them into this top one, if I say 7 equals 2 times 1 plus 5, well 2 times 1 is 2, plus 5 is 7, so 7 equals 7. So you can check real quick to see if this solution works. And in this case it did. So that's the substitution method. Now in example 4, which I'm going to have you try on your own, so you'll pause the video here in a second. First and foremost, you're going to have to solve one of these equations for either x or y. And personally, I'd probably take the top one. That's what I'll do. Solve that for, in this case, I'm going to solve it for x, and then I'll substitute it into here, and ultimately solve for y. So go ahead, pause the video, give this a try, and then come back and I'll explain it. Okay, so you should have given example 4 a try. And what I said first is I was going to solve this equation for x so that I'm able to substitute. So I'm going to bring this down here. X minus y equals 3. If I solve for x, if I want x alone, I'm going to move this y over. Add. That means I'll get x equals y plus 3. So now this is solved for one variable, which I'm in business, because now I know that x is the same as the expression of y plus 3. They represent the same thing. So I can take this y plus 3 and put it in for x, or substitute it in for x in this second equation. That way I'll have an equation in only y, and then I can solve for y. And ultimately after that, once I know y, I can solve for x. So let's go ahead and do this. So I'm going to copy down my original problem. X plus 2y equals negative 6. I'm going to put y plus 3 in for x. Y plus 3. And then I'm going to write down everything else I still have. Plus 2y equals negative 6. Again, combine like terms. I have a 1y here, and I have a 2y. That gives me a 3y. I still have this 3 here, so that I still need to add. So 3y plus 3, and that's going to equal negative 6. Now it's a matter of solving a two-step equation, which we should be proficient in at this point. So trying to get y alone, subtract 3, subtract 3. These cancel. We're going to be left with 3y equals, so now I have to be careful here, negative 6 minus 3. Or negative 6 plus negative 3 would give me a negative 9. There's your integer operations again. Like I said, none of this stuff goes away. In order to get y alone, divide by 3, divide by 3. Y equals negative divided by positive is a negative, so y equals negative 3. Like I said before, that's half of my solution, so negative 3. And this is right solution here. Now we need to solve for x. And I think that what I want to use, I'm going to use that top equation of x minus y equals 3. You could use both of them. They should give you the same answer for x. But I just think the top one's going to be a little bit easier to work with. So I'm going to, so x minus y equals 3. Now I'm going to get an equation in terms of just x. And I know in this case that y is equal to negative 3. So I'm going to substitute that in for y. It's going to replace it. And we will have x minus negative 3. Be careful because that minus stays there. And you're just putting negative 3 in for the y. And that equals 3. So I will have, if I rewrite this, I will have x plus 3 equals 3. Now I need to solve for x minus 3 minus 3. X is equal to 0. So my solution is 0, negative 3. Now for the sake of time, I'm not going to plug this into here to see if my solutions work, but that's something you should absolutely do in order to check. It's a foolproof way to know if your answer is right or not. So I highly encourage that. So that's substitution. And last but not least, we're going to work with elimination, which is probably the most complex version of this. But ultimately, all of these versions give you the solution or where the two lines intersect. Alright, so we have a bunch of different versions of elimination we can use. And elimination kind of works like a addition or subtraction problem. So what I'm going to try and do here is with elimination, it sounds exactly like what it means. You're going to try and eliminate one of the variables in order to solve for the other one, and then plug that value back into one of your original equations in order to get the other one, and hence getting your solution. Again, that's a mouthful. So let's rewrite this, and I'll show you what I mean. So we have 4x minus 3y equals 5, and negative 2x plus 3 equals negative 7. Now this one, what I'm noticing here, oh I forgot this y, whoops. I'm noticing here is I have a negative 3 and a positive 3y. Well, that's going to cancel, so I'm going to set this up as an addition problem in order to solve this. So now what you're going to do is just add down the columns here. So 4x plus negative 2x. This is where integer operations are going to be very important. You're really going to need to know these here. So for x, let's do 4 plus negative 2, which would be 2x. Negative 3 plus a positive 3, which is just negative 3 plus 3 is 0. So 0y. There's nothing there. We don't have to write it. And that's going to be equal to 5 plus negative 7. So think about that. 5 plus negative 7. If I do the bigger minus the smaller, I do 7 minus 5, which is 2. And then there's more negatives, so my answer is negative 2. Now ultimately, I just have to solve for x here, because I eliminated y. It's gone, hence elimination. We got rid of it. So let's go ahead and divide by 2, divide by 2, and x will be equal to negative 1. So again, we have the first part of our solution, our ordered pair where these two lines cross, where they meet. So negative 1. Now you might be thinking, well, how do I find y? Well, we're going to use substitution here, and we're going to substitute this negative 1 into one of these equations and solve for it. And typically I look for the one that doesn't have any negatives that I have to deal with. So I'm going to do this one up here. So 4x minus 3y equals 5. I'm going to substitute negative 1 in for x. So 4 times negative 1 minus 3y equals 5. 4 times negative 1 would be negative 4 minus 3y equals 5. So we're trying to solve for y here, so I'm going to add this 4 to both sides. And those cancel. I'm going to get negative 3y equals 9. Divide by negative 3. Y equals negative 3. So my solution to the systems of linear equations using elimination is negative 3, or negative 1, negative 3. Again, you could plug those values in and you should get 5 and negative 7 being equal to each other if you did it correctly. This version here, example 6, is going to use subtraction, because I see here already that 7x and 7x, they're both positive, but in order to get rid of it, we want to subtract this whole thing. So we're doing it like a subtraction problem. We're going to have to really pay attention to signs here. And noticing that these things are addition or subtraction is just going to take some time with you practicing these problems in order to get it. So if you don't get it right away, that's fine. Not a big deal. I don't expect you to. So we're going to subtract this, and we're just going to go down our column. So 7x minus 7x is 0x. I'm not even going to write it. Here's where we got to be careful, because this is going to be a keep change change problem. So we're going to have negative 2y minus negative 3y, which is really negative 2 plus 3y. So I'm going to get a 1y equals, and we do 5 minus 4, which is 1. So this one was real quick. We know that y is equal to 1. So we have half of our solution again. So let's go back up here and get our solution going. So 1. We know that our y value is 1. Now we're going to substitute this 1 in for y into one of these equations. These are kind of a horse apiece, so I'll just use the top one. 7x minus 2y equals 5. We're going to take this one and replace y with it, because we can substitute it. They mean the same thing. Y is negative 1. They're equivalent to each other. So let's rewrite this. 7x minus 2 times 1 equals 5. 7x minus 2 equals 5, because when we multiply those, And I need to add 2 to this side, add 2 to this side, and we will get 7x equals 7. Now if I divide on both sides by 7, I will get x equals 1. So the solution to this problem, or the point where these two lines intersect, is at the point 1, 1, up in the first quadrant. So there's that problem. So elimination is a little bit more involved, and it can be trickier to see what two terms will cancel out with each other, or which ones you can eliminate. Now sometimes, so that's example 6, I will go through example 7 because this is another version of it, like I said in our goals at the beginning of the lesson, using multiple versions of elimination. Now sometimes before we can add or subtract, we have to multiply one of the equations by a number. Sometimes you have to multiply both of them in order to get something that will cancel. So in this case, and sometimes you can set them up so that they'll eliminate right away after you do this. I'm just going to rewrite this problem quick. 4x plus 3y equals 8 and x minus 2y equals 13. So right now we see that none of these things will cancel out because there's not two numbers alike like there were up in these examples. So we had negative 3y and positive 3y. We could make 7x and 7x cancel just with subtraction. Well, down here we can't. So what we're going to need to do is change this x or this y in either of these so that they'll cancel. And what I'm noticing right away is that x is going to be easiest to cancel because there's a 1 in front of here. And if I want this to be the same number or the opposite number, I should say, so 4x, I need to multiply everything here by negative 4 before I can actually do the elimination process. So there's an extra step here. So if you're confused right now, it's okay. There's a lot that's going on here algebraically. So let's rewrite our first equation, 4x plus 3y equals 8. If I multiply through here, remember we have to distribute. Don't forget that. I'm going to have negative 4x plus 8y because negative times negative, negative 4 times negative 2. And then 13 times negative 4 is, I want to say it's negative 52, I think. Yeah, negative 52. So now we can do elimination here because our 4's will cancel, and we're going to use elimination using addition. Because if I do 4 plus negative 4, I get 0. So we don't have to write that. 3 plus 8 is 11, 11y, and that's equal to 52 minus 8. Well, if I subtracted 10, is it negative 44? I think that's what it is. Yeah, so negative 44, sorry. Negative 44. So all of these should work out to whole numbers. Typically, you're not going to get goofy ones at this level. So if you ever get a goofy number, you probably want to go back and check to see if you made a mistake. So if I divide by 11 here on both sides, I'm going to get y equals negative 4. As I said before, we have half of our solution here, so we need to find x. Let's substitute this back into one of these equations. Since we haven't ever used the second one, I'm going to use that, and because it looks a little bit easier to work with. So x minus 2y equals 13. So let's take that negative 4 that we got down here, substitute that in for y, and we can solve for x. So I will have, I don't want to use this marker, x minus 2 times negative 4 equals 13. Negative 2 times negative 4 is a positive 8, so I'll have x plus 8 equals 13. If I subtract 8 from both sides. These cancel. X is going to be equal to 5. So our solution in this case is 5, negative 4. And as I've mentioned in all the other parts, if I plug these two values back in here, I should get 8 and I should get 13. So if I put 5 in here, that's 20. 4 times 5 is 20. Plus 3 times negative 4 would be negative 12. 20 minus 12 is 8, so that one works out. So you can go back and check those. I highly encourage that, but for the sake of time, I'm going to stop the seminar here. So make sure this foldable gets put into your notebook, as it will be a huge reference for you with the probably most challenging topic of the year. And if we just recall real quick, today we worked on solving systems of linear equations. Our goal and I can statements are listed here. Hopefully you're feeling comfortable with most of these. If not, you can always rewatch the video to see what I did. And as always, please ask me questions whenever you are stuck.